Hello everyone, welcome to my video. In this video, I will cover section 2.5. We have learned the XY or Cartesian coordinate system in the previous section, which is especially convenient for analyzing horizontal or vertical motions. However, when I'm interested in a certain moment or a specific point on the moving path, the normal and tangential coordinate system would be more useful depending on what my interests are. For instance, I do not care where the object is. I simply want to know the velocity and acceleration at that point, at that instant. For any curvilinear motion, the object will move with the path, and the path will have a center of curvature C and a radius of curvature ρ. Connecting any 2 points along the path to the center of the curvature, we can have the normal direction. And then we'll draw a perpendicular line to the normal direction. We'll have the tangential direction. So knowing the two basic directions in the NT coordinates, that's where the n comes from. N is normal, T is tangential. Just like the I and J in XY system, we also have the two unit vectors in the NT system. En, the normal unit vector, and Et, the tangential unit vector. For any 2 points on the path, say A to A prime, our object's location change can be represented by a very small angle change, d beta. Knowing the radius of curvature is ρ, we can calculate the arc length, which describes the path from A to A prime, ρ times d beta. We're moving along the path, so the speed we're observing is along the path, which is a tangential direction, vt. Now we have the displacement, we can take the time derivative to get velocity. Note that the velocity we are talking about here is a tangential velocity. You can also see that here we represent it as a scalar times vector form. The scalar is a speed, the magnitude, and the vector is the unit vector telling us the direction is tangential. I will spend some time on the next few slides to focus on the conceptual part before going into explaining its practical value. With the velocity known, we can take further time derivative of it, which now gives us the acceleration, the general acceleration. But there is a problem here because Et, the tangential unit vector, is changing with time. So it won't cancel out or it won't become zero during a derivative, since the object is on a curved path. So we need to take care of the unit vector Et, find out what is the derivative of Et. Looking back at the diagram, we have tangential velocity at A and A prime, V and V prime. Since they are vectors, so we can move them tail to tail. If we do so, we replace the velocity vector with a unit vector just to focus on the direction of the movement. Essentially, from A to B, our Et becomes E prime t, and the difference between these two vectors are d Et, as shown on the diagram here. Looking at an infinitely small time interval, the det is equal to the length of the arc because it's so small, which is a change in angle d beta. Also, for this super short time interval, the direction of det can be considered as perpendicular to et. Recall from the beginning, in the NT coordinate system, et and en are perpendicular to each other. So this means the direction of det is the same as en. So we have a magnitude and we have a direction. Now we can put everything together. Our det is equal to en, the unit vector of the normal direction, times d beta, the magnitude. Almost there. With this det equals to en, d beta relationship, let's divide both sides with dt. From a few slides ago, we had v is the velocity is ρ, the radius curvature, times beta dot. So combining everything, we obtain the time derivative of et. Going back to our derivative of the velocity when we got stuck because we didn't know what is the derivative of et, now we can put it together to get our overall acceleration. which is described by two directions, tangential direction ET and normal direction EN, or two components, the n component and t component. We can separate this vector expression to look at its scalar form. The normal acceleration can be calculated by v squared divided by rho, and the tangential acceleration will simply be given by the velocity. In any curved motion, when we say velocity, we are actually referring to the tangential velocity. So I would like to call this observed speed. So the total acceleration is given by combining the normal and the tangential acceleration. Please allow me to use this slide to reinforce what I just said. In any curvilinear motion, there are two directions we need to use to describe the motion: normal direction and tangential direction. The normal direction is vertical to the path. It does not affect the speed, but it do affect the velocity, will change its moving direction. And the tangential direction is along or parallel to the path. This is the observed speed or observed velocity. Looking at the normal acceleration equation here, an equals to v squared over rho, the velocity in this equation is the tangential velocity or the observed velocity. As that being said, please take a moment to clearly distinguish these three variables, an, at, and vt. At affects the magnitude of vt, and at also affects the tangential direction of vt. An, on the other hand, it only affects the direction of vt and does not affect the magnitude of at. It only changes the direction. Among all different curvilinear motion, there is a special case when the path is a perfect circle. In this case, we call circular motion. Our previous derived equation can be simplified since the radius is a constant now. Please note here we also updated the symbol for the angle and radius curvature, and theta and r, they are just specially for circular motions. Also, as a reminder, always work in radians. Always, 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 please. This concludes our section 2.5. Please read the recommended material as listed here. Thank you for watching. I'll see you next time.